All right, welcome. For those of you who will watch this in the future, because I don't think anybody's going to watch right now. Who knows? This is another of my Erik Learns in Public videos. I'm just trying to do these super regularly because this is some things I want to make sure I keep studying consistently, and this forces in the discipline doing it. And if anyone can ever benefit because of me going through some of this stuff, that's awesome. There's a lot of mental rambling and working stuff out. This isn't stuff I know well, some of it. And so when I'm presenting, I'm not presenting as an instructor. I'm just learning as a student. So welcome to my world. All right, so here's what happened is I've been studying data structures and algorithms for a little while. And parts of it I get really well. And I was embarked on some study, a regular study of it about 3 or 4 months ago, and I just stopped. And I picked back up where I was, and I realized that the reason I stopped was there was actually just a word I misunderstood. It's all about logarithms. So for context, what I was looking at is just when you're looking at different algorithms in computers, and you're analyzing them for the complexity of how much time the algorithm might take up as the size of the input increases, this whole big O notation area. And I got to the point where we talked about the time complexity of log n, and I just stopped studying, and I couldn't quite get it. So I figured it out finally, and it's simple and it's awesome. But I wanted to start with this word logarithm because this really surprised me. So let me share my screen and just look at some nerdy math stuff. I hope this comes across well. Still getting used to using this particular drawing app. So this whole logarithm thing, the equation for it log, depending upon the base your number system uses, of x is equal to y, where we're going to know what x is. And this is true if and only if the base power of y equals x. Now I'm going to see if I got that right by plugging in some real values. Let's try log base 2. We know this number. I'm going to go 4 is equal to what? Y. Well, then I've got the base is 2 to the power of y equals 4. Well, 2 to the power of 2 equals 4. So log base 2 of 4 is equal to 2. Okay, so I can talk about it relatively fluidly right now, but an hour ago I wouldn't have been able to. And part of the reason why is because it has to do with this word logarithm. I looked up the word, and I'll look it up right now. Nothing special here, just go to dictionary.com and look up logarithm. And it says the exponent to which a base number must be raised to equal a given number. And let's circle some of the things that matter here. The exponent, that's this, this, this. Here, okay, good. To which a base number, here's my base. This is supposed to be a 2, in fact. So erase that, go back to black, write the 2 there. So here's my base. Here's my base. I didn't mean for all that to be red. So exponent. Exponents are red. If I got this right, yeah. There's all my exponents. Now let's look at the base, and I'm going to circle base in blue. Here's my base, it's base 2. The number system uses only 2 symbols, 0 and 1. Here's my base, here's my base. So the exponent to which a base number must be raised to equal a given number. Well, the given number, we'll go green. This is the given number. It's 4. So this is true here. The logarithm for the given number, 4, if we're looking at base 2, the logarithm is a 2. So again, I'm talking about this pretty well now, but I wasn't a little while ago, and the reason for it is the derivation of this word. I'm going to pull this over here, and let's just talk about logarithm for a second. 2 words. See something a little darker. Logos, from Greek, I'll come back to that in a second. And then it's down here. And arithmos. Now this is pretty clear. Arithmos means number in Greek. But logos, this was a lot more difficult. When you look it up, in Greek, it can mean a lot of different things. And in fact, derivation, it just says a Greek word, see logos. And it just says a combining form appearing in loan words from Greek, where it meant word or speech. So I tried that out. I went, well, wait a minute. If this somehow means word or speech number, word number, utterly unhelpful. So I started digging into it a little bit more. I found something pretty interesting. I think this is on my new browser I'm using. Here it is. Found some site out there called Wordsmith. And there's an article about, of all things, actually not surprising, the Gospel of John and the Bible. And in fact, it talks about something that anybody who's read the Bible is familiar with. In the beginning was the Word, and the Word was with God, and the Word was God. And I went, well, that's interesting. I read the Bible a lot. So then he goes on this tangent here, or not tangent, it's an explanation of logos. And he says in ancient Greek, logos had many meanings. Points out that none of them is truly to be understood as word. He talks about the translations that happened over time. But then he says, the Greek word logos designates the power of reason, the pattern or order of things, the principle of relationship. And now it's starting to get a little more clear. And an organized articulation of something. He says, in general, it has the following meanings. 1, order or pattern. 2, ratio or proportion. Now I'll go over the others, but this is where it really started to make sense. Ratio or proportion. He talks about other meanings. It's got a lot of them. There's a thing called an oratio, O-R-A-T-I-O, a discourse, an articulation, an account, telling a story. It also meant reason, and it meant principle or cause, a principle of mediation and harmony between extremes. Logos meant a lot of things. That's fine. We have a lot of words that mean a lot of things in English and other languages. But I looked at that ratio proportion, and then I looked at what we're looking at math-wise and went, oh, there is a ratio, a proportion, a relationship between the number we're looking at. In this case, I'm going to say a given number. I'll switch back to green. Here's our given number. And there's a ratio between it and an exponent. And you can see that relationship. If we make a new page, and look at this same thing. Now, I'm going to assume base 2 on all of this because we're dealing with computers, and computers are base 2. I'm not going to get into base 10, decimal, all that kind of stuff. But let's look at log. I'm even going to write the 2 of 2. And we'll look at log of 4. And we'll look at log of, I'm going to go pretty high. We'll go 16. I haven't done the math on some of these. This will be fun. 32. I skipped 8 for anybody who's a binary nerd. So what is the log? Well, we know that this is 2 to the power of y equals whatever we have. 2 to the power of y equals 4. 2 to the power of y equals 16. 2 to the power of y equals 32. Well, we can do this. 2 to the power of 1 equals 2. 2 to the power of 2 equals 4. 2 to the power of 4 equals 16. 2 to the power of 5 equals 32. So we can start to see a ratio. We can start to see a relationship. Our given number over here on the log side of things is related to the exponent. So we see this relationship. Let's fill in the actual answers. That's 2 to the power. Let's see if I got this right. So it's 1, 2, 4, and 5. 1, 2, 4, 5. And now we start to see a distinct ratio. And this is what clued me into why it's even valuable in computer science and algorithms, is I started to look at this ratio, this relationship. And I went, well, let's look at that bad boy on a graph. We have here n. This is our input. Our input is growing ever larger. And this is the number of operations we'd have to do. So if you've got some sort of algorithm and we look at number of operations getting bigger, what's interesting is as n gets really large, we can see here, what if n were like 1,000,000? That's a really horrible m. Well, fine, it's 1,000,000. The log would be some number. I can pull out a calculator. I don't care. What's important here is, what if we doubled the input and went to 2,000,000? This answer only goes up to whatever it is, plus 1. That's all, plus 1 more. So if for a given input increasing dramatically, we see a very tiny increase in the number of operations required to accomplish your work, that's pretty good. So we could see that at the very beginning of trying to handle some data, the number of operations might go up pretty rapidly, but then as n gets larger and larger and larger and larger, the number of operations we need to handle it only goes up a little teeny tiny bit. I just compared that to the idea of operations that take constant time. It's a nice straight line. Wow, I did pretty good there. I went, man, constant time is great. No matter how big the input is, it takes the exact same amount of time to do your operation. But you don't find many cases where the data you need to process will play nice with that approach. So that helped. And again, going back, is because I finally cleared up this whole section over here. I'm gonna mark it off in green because I like it so much. What in the heck does this word logarithm really mean? It's an examination of the ratio or proportion between a number and its exponent. Now, I'm sure the math nerds would have a much more precise explanation and terminology, but I don't need to know all that. What I need to know is, if I have some sort of an algorithm that I can use and a data structure that'll work well with it, where every single time there's a massive increase in the n, the amount of data that I'm handling, but the cost of processing that data increases only according to a logarithmic scale, that's a really, really good algorithm. That's what I cared about. Another interesting aspect of it is that I started to realize that the approach taken here, like when would this be suitable, paralleled a way of thinking I've had as an engineer, as a nerd for a long time. And by the way, the clearing up the word I did, but the source for some really good background on it is algoexpert.io. Algoexpert.io, they're awesome. That was a video I abandoned months ago and then went back to and went, oh, I got it. But he talked about two different examples. He talked about an array. These are the elements in the array. It's got 8 different elements. Let's make a 0 at the beginning. Here's the elements in the array. And he said, never mind the specifics of the implementation. He says, if there's some sort of algorithm you can feed this through, that in applying its work, the very first operation you do can split the data set that you need to examine in half, fully eliminating half of it, you've got a logarithmic situation. And you did the math on it, which I'll do. First operation, so put number of operations, we have 1, there's a tick mark. We eliminate all of these. Second operation, we take the remaining 4 elements, cut them in half, or 2 operations. And let's say we eliminate everything over here. Final operation, there's a tick mark. We eliminate one of these 2. It happens to be this one, and we find what we want. Again, I'm not using a specific algorithm or a specific set of data. I'm just talking about the concept. So we have 3 operations. N, or our size of our data, equaled 8. And the operations was 3. And you say, watch this. What if our algorithm had 16 elements? 0, ... 8. I'm sorry, 7. Which is what we had before, but then all the way to 15. I'm not drawing them all out. We have an array where n equals 16. How many more operations do we need? 1. The first operation eliminates everything over here. And then we're back to the split, and then the split, and the split. So we have 4 operations. So n has doubled. It's 2n. Therefore, it's 16 as the input size, but our operations only went up by 1. This is logarithmic efficiency. Log of n efficiency. And I went, okay. And what it reminded me of is something I learned in the Navy a long time ago when you're dealing with a complex system with interrelated parts, because you could have some sort of overall system, an electronic or electromechanical system. In other words, you've got some parts that are electronic and some parts that are mechanical. This happens all the time in the Navy and other industrial applications. And so here's all of these parts. This might be a circuit. This is E for electricity. This might be an actual physical device. I'll put M for mechanical, but it has some wires that connect it. You're maybe detecting something that's happening mechanically. There might be other electronic systems that we need to interact with, and even other mechanical devices. And there might be electronic systems that tap in to some of this traffic back and forth. This is even a simple diagram. You can see it's 5 different things going on. It's quite complex. And the approach that I learned at this was called Electronic Technician Maintenance School, this really awesome school I went to in the Navy. It was called half splitting. And the concept is, how do I eliminate at a stroke half of the system? Let's reverse that and talk about a little more precise. That is, this system has some sort of input that comes in and output that comes out of some nature. And somewhere, something's going in correctly, but what comes out is wrong. The system's misbehaving. A faulty piece of equipment. You look at the exact nature of what it is that's going wrong and find a point in this big complex system where if you set up a test with some known conditions and you determine what's happening at that spot, you can, in one fell swoop, figure out whether the problem lies before or after it in terms of this complex system, thereby splitting it in half. So let's say in this instance, you performed a test where that red dot is, and you found that what you expected to have happen here for a given input was wrong. You didn't get what you wanted. Well, we know that by the time whatever work we're doing makes its way through these systems and it gets here, it's already wrong. That means we don't need to look over here at all. That's not where the problem is. Now, yeah, you have to have an understanding of how the system works, how these different parts interrelate. But that's your job, is to understand the system. Having understood it, now we can see, well, somewhere in this whole section right here is where my problem lies. All right, let's find a spot about halfway again. Let's test right here, right after the point where another system is connecting. And let's find that everything there, I'll use green, is exactly what we expect it to be. There's no problems. That means we don't care about these parts. And we know we have found our culprit. Somewhere in here, something's going wrong. And I use this all the time when repairing electromechanical equipment. It was awesome. It worked really well. And I use it in debugging what's going on with a complex system. It's a software system. Understand the system, find out where a known input comes in, about halfway through, test whether you're getting what you expect. And that tells you which direction to keep on going to track down the problem. So this half splitting thing was awesome. Use it a lot. And I went, oh, well, oh, maybe it's farther up. That's exactly what's going on right here. We're half splitting. We're in one swipe, finding out what parts of this data that I'm processing do I not need to look at anymore. Instantly with one check. All right, so then I went, well, what kind of data structures lend themselves to this? Well, I guess you could figure out some way that an array like this would be in a condition such that you could, in fact, eliminate half of it with one operation. But the data structure that really started to make sense was one I was studying last year and made a lot more sense, which is a binary tree. And that's the code one I'm going to do in a minute. It's a data structure where you have an element that's a root. There's a few different variations on binary tree. I'm just going to talk about one called a balanced tree. This is a parent node, and every single node has two children. That means this one could have two children. This one has two children. Now, if I want to add more data, I add it in like this. And every single one has two children. Well, if a binary tree is arranged in a set manner, and we can control that, when we're running an algorithm, we're doing some unit of work in processing this tree, it's quite often possible to, at a glance, just decide, say if you're starting here, whether you're going down the left side of the tree or the right. And if you end up, in terms of your search, knowing just from one simple evaluation, comparing this node to this node, that you need to go down the left side, you instantly know you don't need to process the right side. You've done this half splitting thing I'm talking about. And you're in a logarithmic situation. Because if you were somehow to need to add, I'll put the additional nodes at the bottom here so they stand out. New nodes on everything, you have now 2x'd the number of nodes you have. You've doubled the number of nodes. But your number of operations that you have to run your algorithm through only increased by 1. Because by the time you get down, say, to this exact node, you still only got to decide between two different things. That's one more operation. Now, again, those of you who are computers, data structure and algorithm experts are probably like, Erik, duh. Well, I didn't understand it. And I ain't stupid. And now I do. And I really like it. So I kind of want to just share my journey. I'm going to go back and reinforce it for both me and you. The equation for a log for a given base is log of base in base b of a number x is equal to y if and only if that base raised to the power of y is equal to that given number. That is our equation. We looked at a few examples of it. We said, well, we're assuming base 2 because we're in the binary system, which only has 2 digits, 0 and 1. And we said if a given number is 4, we need to solve what the log is. Then we can go, okay, well, our base raised to the power of what would equal 4? Well, 2 raised to the power of 2 would equal 4. So we know our log is 2, and that's what's right here. And we cleared up the derivation of this word logarithm. Logarithm, yeah, strictly from a math nerd standpoint, the exponent, y, to which a base, there's the b right here, must be raised to equal a given number, x. Fine, that's a nice nerdy math definition. What does logarithm mean? That. Where does it come from? Greek. Logos, meaning proportion or ratio, and arithmos, meaning number. So we're dealing with ratios or proportions for numbers. And we looked at what that means for complexity of an algorithm. We saw that as our inputs right here get very, very large, the number of operations required to process it only increase incrementally in a much smaller ratio. There we go. And the graph, as n increases, the complexity or number of operations needed would start to rise very slowly as our inputs got larger and larger and larger. So an algorithm that can operate at the big O notation O of log n is a really, really, really good algorithm. And we looked at 2 different examples. One, a little less likely. You'd have to have a perfectly structured array where the data was such that a single operation could eliminate half of the data from consideration. But then we looked at one that, by its very construction, means that a lot of operations in it will be at a big O of log of n, where the number or the size of the problem increases. The number of operations, the order of magnitude of the problem, only increases logarithmically. And that is the binary tree, if properly constructed. That really helped me. And I hope it helped you. Maybe you didn't have any problem with this and you already understood it. I didn't. So references I recommend are algoexpert.io. Really, really, really great explanation of this. But also, if your basic math is a little off and you're not still 100% on some of that, well, what's a number system? Like, what does a base mean? Do a little research on that. This IAF just means if and only if. It's a bit of a logical sort of comparer. But I hope that helps. I'm super, super glad I figured it out. And I feel like I can continue with my studies. So there you go. That's my stream for the day. I'm going to try to keep on doing these pretty much every day, because that's the other thing that I was reading in a really, really great book about the self-taught computer scientist. There's another reference. Let's look that bad boy up. I'm going to put it on screen because I think you'll like this. Let's pull that because I'm sharing. First things first, I'm going to pull up that algoexpert.io. Highly recommend these. What I have is Algo Expert. They also have Systems Expert, Machine Language, Front End. Algo Expert's awesome. But this is called Self-Taught Computer Scientist. Ah, that was by Cory Althoff. This book rocks. Here I've written a great book called The Self-Taught Programmer, which I'd seen before, but this is just phenomenal explanation. So here's the point is, in here, he addresses right in the introduction the dedication needed to get through something like this, and talks about this thing that apparently Jerry Seinfeld came up with. I believe that I can actually look at this inside my Amazon account. So I'm actually going to pull it up and do my Kindle reader. Yeah, that's what I should do. I'll do Kindle Reader Online, Kindle Cloud Reader. There it is, because I was just reading it. I'm going to pull this up. I want you to see this. Yeah, logarithmic time. That's what I was reading. Yeah, here it is. Sticking with it. Jerry Seinfeld invented "Don't Break the Chain." He came up with it when he was crafting his first stand-up comedy routine. First, he hung a calendar up in his room. I might actually get a paper calendar, which I haven't owned in years. Then, if he wrote a joke, at the end of each day, he gave himself a red X on the calendar for that day. That's it. Once you start a chain, 2 or more marks in a row, you will not want to break it. Man, it's just so simple. Well, I streamed yesterday doing this. Again, I have no idea if anybody's going to watch these, but it's helping me. So I'm going to keep on doing it, and hopefully it'll help others. And I'm just going to do this every single day. Now I don't want to break it. So there you go. I'm learning in public. I've been a software professional for decades. I know how to program. I know how to do my job, but there's just things I don't know. And it's true for anyone in the industry. So whether you're at the beginning of your journey or you're an experienced engineer, I hope this helps. That some of the things, I hope you're going through similar things when you're trying to learn new technologies. I just happen to be learning this data structures and algorithm thing. So I wanted to share it. That's it. Have a wonderful day or evening or whatever time it is for you. And I'll see you on these soon.